Okay, so hello everyone and welcome to this pre-recorded presentation on the application of acoustic and ultrasonic devices in the characterization of blockages and defects in underground pipe networks. So in terms of the motivation of this work, we rely heavily on huge underground pipe networks to support urban life. There are 600,000 kilometres of underground sewage pipes in the UK alone, many of which are old and in deteriorating condition. So it's important to have the tools to monitor their condition and to detect faults early on prior to catastrophic failure, so these systems can stay in constant use. Specifically, we're looking at the application of acoustic and ultrasonic methods here. So the acoustic device is low frequency and is used for detecting and classifying blockages at long range. And then the ultrasonic system can be deployed at short range to produce high resolution scans of the blockage. This has some potential advantages over traditional video CCTV methods. So rather than having to manually inspect the footage for small defects like cracks and holes that you might miss, you get direct spatial positional data, so you can't miss these features. It's also potentially strong in low visibility situations, such as dust or smoke. So here's an overview of the acoustic system. It's basically a loudspeaker to emit a pulse down the pipe, which is then reflected by the feature and picked up by an array of, in this case, 9 microphones to capture the echo and analyze it. This is for ranges at around 10 meters, that kind of order. And the fundamental challenge here is how do you distinguish between an echo from the pipe end or an intersection of pipes and something that's a problem, a blockage. So to give us some initial insight into this, we implemented a finite element acoustic model in COMSOL. This consists of a monopole source centered in a pipe of diameter 150 millimeters, and it emits sound towards a blockage or a feature at 3 meters. 2 cases were simulated here. There's a half blockage and a T-junction called a lateral here. So as you can see on this plot down the bottom, the reflection coefficient was calculated at a range of frequencies, and for most of this frequency range, there's a higher reflection coefficient for the blockage compared to the lateral. Up to this green dotted line, which represents the cut-on frequency for the pipe, past which high frequency modes dominate, up to this point, the reflection coefficient increases for the blockage and decreases for the lateral. And past this point, there remains a large difference between them. So this suggests good sensitivity to identify the two of these. So experimentally, a loudspeaker was used to emit a chirp signal covering the frequency range 100 to 6,000 hertz at a target 9 meters away. That target again was in one case a blockage and in one case a lateral. The signals were then bandpass filtered between 300 and 2,000 hertz to remove higher modes. So down at the bottom there is the impulse response time trace. And as you can see, there are weak reflections from the joints between the pipes and much stronger reflections from the features. As predicted by the finite element model, there's a much higher amplitude reflection for the blockage compared to the lateral. And these are also located to about within 14 centimeters, which is quite good for this frequency, and the ultrasonic device will be able to then pinpoint it more accurately. So a benefit of testing using a chirp signal is that you can see the response across a range of frequencies. So on the left there is just a close-up of the 2 signals from the lateral and the blockage. You can see the blockage is much higher amplitude. And then the middle plot shows how the sound pressure level of the reflection varies with the frequency. So past the cut-on frequency of the pipe, you can see that there is a wide gap between the two, between the blockage and the lateral, with the blockage producing a higher amplitude, as expected. Another potentially useful thing is the phase response is different. So as you can see on the right there, the blockage experiences a much greater phase delay, and this only increases as you increase the frequency. So in terms of the ultrasonic system, the purpose of this is to produce high resolution images at close ranges of about 10-50 centimeters. And these photos show the experimental device that we built and are testing. It consists of 140 kilohertz transducers that fully occupy a pipe of diameter 150 millimeters. This is more elements than would be practically deployed, but the purpose is to determine an upper limit for imaging performance. And because it's set up to record full matrix capture data, which consists of time domain signals from all the possible transmit-receive pairs, this means we can downsample the data to give results and images from any subset of the array. So we can see what images from a 20-element array look like. And that allows us to investigate one of our main objectives, which is determine the trade-off between reducing element number and reducing image quality. So figuring out how few elements we can get away with for a usable image. So one of the first things we did with this experimental device is to determine if it was working as expected. And we did this by experimentally measuring the point spread function by imaging a small 3mm bead at a range of 20 centimeters and comparing the image to that from a Huygens model simulation. So there's the experimental image on the left and the simulation on the right. And as you can see, they're in good agreement down to about -25 decibels, which was deemed acceptable. They were also compared in terms of API, Array Performance Index, and this is basically the area of the -6 dB footprint. They're quite similar values here, 2.70 for the experimental and 2.33 for the simulation. So here are some example images from inside the pipe. We 3D printed a plastic cylindrical blockage that fits neatly into the pipe and is cut into 10 layers, so we can make a variety of different blockages and see how it images all of them. So on the top there is an image of a semicircular blockage, and on the bottom is a 2 centimeter wide bar in a couple of different orientations. So as you can see, it gets the position and shape quite well, but there is a persistent artifact. So you get a strong reflection in the center of the pipe and right at the wall, but in between the two there is a dead zone of low amplitude. We suspect this is to do with the interference between reflections from the dead zone that come directly and those which return via a collision with the pipe wall. This effect seems to depend on range, which makes sense with this reasoning. So as you're imaging things at a greater range, as it moves further away, you can see that the central region of the bar goes from being wide and rectangular to narrow and more circular. So the dead zone widens as you get further away. So moving on to testing the performance of lower numbers of elements in the array. When selecting, say, 25 elements out of the possible 100, it matters which 25 you pick. The different arrangements will perform differently, and some will be much better than others. So it's important to identify the ones that perform best. And we did this through running a PSF, a point spread function imaging test for several thousand randomly selected arrangements grouped by the size of their aperture. So this plot on the right here shows how each of these random arrangements scores in terms of signal strength, represented by signal to noise ratio on the x-axis, and in terms of resolution, shown by API on the y-axis. So a tight resolution is represented by a low API. So it's desirable to be in the bottom right corner of this graph, because that means you've got strong signals and a fine resolution. And in this region, it is largely dominated by the groups of largest aperture. And as you decrease aperture and restrict the elements to the most central region of the pipe, represented by the yellow scatter points there, you are reducing your performance. You're getting weaker signals and a worse resolution. However, the point spread function alone is not enough to guarantee good general imaging performance. So we combined this with another metric, which is the percentage match of an image to a reference image. Specifically, we're comparing the -6 decibel contour of a bar object and calculating the percentage match to the image produced by the full 100 element array. So here are the results of percentage image match for several different element numbers, 16, 25, 32, and 50 for all these aperture groups, shown as a distribution of their percentage match score. And it basically comes down to a balancing act of element density and aperture size. A larger aperture, as we've seen, produces a stronger and finer resolution on the point. and this is shown by in the 32 and 50 graphs there. The groups which perform the best at the highest percentage scores are those with wider apertures. But as you reduce the element count, for example, 16 and 25 here, the large aperture does not necessarily do well. It's actually the smallest aperture which does the best. And this is because if you go to the large aperture to get that fine resolution with a low number of elements, the elements are too sparsely distributed, and you don't get a good match to the reference image. So the exact number of elements that you can go down to and still get a usable image depends on a lot of factors and the specific application. But in this case, we're getting the most consistent and trusted results past 25 to 32 elements. You can't go too much lower than that. So to summarize all this, we have a two-part system. There's the low-frequency acoustic system that detects features at a long range and distinguishes between expected geometric features of the pipe and unexpected blockages based on their different amplitude and phase response. And then there's the high-frequency ultrasound system that produces close-range, higher-resolution images. And if you're using lower number of elements there, it makes sense to reduce it to a tighter aperture so you have that element density to get decent images. But if you have enough elements to have a wide aperture, you can ultimately reach better performance with this. So thank you very much for listening, and that's the end of the talk.